All right. Happy Friday, everybody. Welcome to the 9th webinar of our GDS webinar series. My name is Jie Ren. I am the sitting chair of APS topical group on data science, and I really want to welcome everybody to today's webinar. Um, so we have, as I said, this is the 9th webinar event of our series. We have captured a pretty large list of fantastic talks, and we have recorded all of them and posted them on YouTube channels. So if you happen to have missed any of the prior event, please go to our YouTube channel, type in GDS APS. You will be able to find all of the recordings. And of course, GDS as a data science group is on social media. So we are established as of April of last year. So we're about 1 year old within the American Physical Society. We are established on the belief that connectivity to data science will help and will actually promote both physics research and education. So if you share similar passion, if you are in the physics community, and if you have a passion to explore data science or learn more about it, please join us. You can find us on LinkedIn, Twitter, Facebook, Slack, or APS website as well. So if you have any thoughts, please also reach us with email. Our official email address is gds@aps.org. So with that, I wanted to also mention that as of now, our topical group is in preparation of the March meeting 2021 sessions. If you have any suggestions or thoughts about session topics or mini symposias, please feel free to reach out to us as well. If you also have thoughts or suggestions on what kind of webinar you might be interested in, or suggested presenters or speakers and things of that sort, please let us know. We are here to serve you, and we are here to help you to get the best, get the most out of data science for.
Audrey, you're muted.
Oh, sorry about that. Yep. And okay, I will just go ahead and introduce today's webinar. We have 3 short talks from PhD students around the world talking about the um, most state-of-the-art data science efforts that they're doing in physics research. So I will turn to go ahead and introduce the first speaker, Leopoldo Sarra, who is a PhD student at Max Planck Institute for the Science of Light in Erlangen. He is a theoretical physicist with a background in statistical mechanics. After graduating in Rome with a master's thesis on spin glasses, he is currently focused on machine learning applications in physics. In particular, one of the main themes of his PhD project is how to exploit artificial intelligence algorithms to automate scientific discoveries. So I will turn over to Leopoldo. Okay.
Okay, thank you for the introduction. So in this talk, I will present our work on unsupervised feature extraction in simple physical models through mutual information maximization. So the idea started with the following question: which are the relevant quantities to describe a system? You know that in physics, there are lots of situations in which the description of a system can be really hard. But if you think on a good representation to look at it, the problem can become quite simple. And this is even more evident if you think at systems like in fluid dynamics or thermodynamics, in which you have a lot of degrees of freedom, but you're able to just look at a few quantities and get all the information that you want to know about the system. So the question is, how can we apply the same ideas in more general cases and find some useful description for systems like chaotic systems or out of equilibrium systems? And what we want to do is to face this problem with statistical methods. So what we do is that we consider our system, our set of many degrees of freedoms, like in a high dimensional space. And what we want to do is to find a small set of quantities that are able to describe this system. So to find a partial description of the system, but that it is as useful as possible. So we find these features using what we call a feature function, f of x, which maps the high dimensional space to this low dimensional space that we call the feature space. The idea would be, for example, if we have a cloud of particles, each of it has its position, its coordinate, for example. One of the interesting features that we would like to find out is the center of mass or the width of this cloud of particles. So some high-level description of this system. So one idea on feature extraction could be to consider a coupled harmonic oscillator system. And for example, we consider its spatial distribution at equilibrium. Our goal on feature extraction could be, let's try to represent this system with just one coordinate instead of two. I mean, in principle, to describe the space configuration of the system, we would need to give the position of the first oscillator and the position of the second oscillator. The question is, what's the best we can do if we want to describe it just with one coordinate? And in this case, we can find the solution in a somehow intuitive way, because for coupled harmonic oscillators, we know that the Hamiltonian is quadratic, so the Boltzmann distribution will be a Gaussian. So what we can do in this case is that we consider the normal modes of the system, and if we want to choose which one gives us the best information, the best description of a given system, we would probably choose the one that has that is in the direction of the largest variance. That is the component that has the largest uncertainty. In other words, if we had to guess the other component, it's quite easier to guess the one that has the smallest uncertainty. So what we would do as a feature, we would choose a feature that projects the two coordinates of the system along the direction of the largest eigenvalue. So our question is, this is a well-known technique. It's called principal component analysis. But we would like to generalize this in situations in which the distribution is more complicated and not necessarily Gaussian. Because indeed, in the previous case, what we were doing was just to consider the correlations among the coordinates and taking the largest eigenvector of this covariance matrix. But if we have something more complicated, looking just at correlations is not enough. I mean, for example, what we would get is something like this if you use the same technique. And we see that this quantity that increases along this direction from left to right, it's not very meaningful. I mean, it doesn't give us a very good insight on the system. So it's clear that we need to use something different. And the idea is to use a quantity that comes from information theory that is called mutual information. This is a quantity that quantifies the dependence between two random variables. And in particular, it is 0 if the variables are independent, and it's greater than 0 if there is a dependence between the two variables. In particular, we would take x as the high-dimensional system and y as our feature that is linked to our high-dimensional system with a function f of x. So the idea is that the best feature that we would extract from the system would be just the one that maximizes the mutual information with the system. So in other words, the best that you can do if you don't put any other constraint is say that we choose the our description to be the one that preserves the largest information with our high-dimensional description. However, there is a problem with this quantity, and it is that it always diverges when we consider deterministic functions of another variable. I mean, this is very easy to see, because if you just rewrite mutual information and as the difference between two entropies, the entropy of the feature and the conditional entropy of the feature given x, you see that this conditional entropy, in the case of a deterministic function y equal f of x, always diverges as a delta of 0, as a logarithm of a delta of 0 for any function that you choose. So even if you consider the optimal function or any other function, mutual information in this case will always be infinite. So one idea that one could have is that we could just neglect this conditional entropy term that is always diverging and just choose the optimal feature as the one that maximizes the feature of the entropy of the feature itself. But we can immediately see that for our purpose, that is the one of extracting a deterministic feature that is also continuous, this is not a very good idea, because it's clear that also this other term that we would neglect, the entropy of y given x, has still some dependence on the feature f of x. So if we drop it, we are changing the optimum of this function. And also there is another problem, and is that if we remove this term, we are losing a very important property of mutual information that is called reparametrization invariance. I mean, in other words, if you perform an invertible transformation on y, so you change the way in which you are representing it, you know that there is no change in information because you're just changing the way at which you look at you're looking at the feature. However, if you just consider the entropy of the feature, we know that this is not reparametrization invariant. So according to the way in which we rescale our feature, we would get different mutual information. I mean, consider the case in which you have a cloud of particles and one of the features is the center of mass. We could get a larger value of mutual information just by rescaling the center of mass, like considering 5 times the center of mass or 10 times the center of mass. But this clearly doesn't have much sense because the center of mass should always give the same information regardless of how you are rescaling it. So the thing that we propose to solve this problem is comes from a physical intuition, and is the one that every measurement that you do always has some uncertainty, like some noise that you have in your observation. And we want to take this into account when we calculate mutual information. So the idea is that before applying our feature, we add some Gaussian noise to the observation, to the high-dimensional system X, and then we calculate the feature. In this way, mutual information is always finite. But then what we can show is that if we remove the entropy of the noise itself, which clearly does not depend on the feature, but just on the Gaussian noise that we added, and we put the strength of this noise to 0 and we perform the limit, we see that we always get a finite quantity, which is the quantity that we can call renormalized mutual information from the point of view that we are subtracting an infinite term in this limit. And we see that this quantity is finite and also respects the reparametrization invariance under the feature. So if we change the feature, this quantity will not change if we perform an invertible transformation. So we can use this quantity, for example, to compare different features. For example, we consider a few features and we want to ask which one is the best to describe the system and when one of those features is the best to describe the system. And I can show you this, for example, in a very simple setting. So we consider a one-dimensional field on a lattice. For example, we have 100 points, and each of those is sampled from some thermal noise, some background noise, and a wave packet with a fixed shape. So each sample is the superposition of those two contributions, some background noise and a fixed shape wave packet. And we want to describe this system. So we could choose a few features and see which of them better describe the system by looking at the normalized mutual information in the system. So one first example could be to just take the mean of the field. And we see that this increases with the strength of the noise. And in some sense, this is reasonable because this is very sensible to the noise, to the background noise that the field has. So if the relevance of the noise increases because we increase the strength of the background noise, then also the importance of this feature will increase. While on the other hand, for example, if we consider the position of the field weighted by the intensity of the field itself, we see that this is more sensible to the position of the wave packet with respect to the background noise. And so this gives more information on the system, but also that this decreases if we increase the strength of the background noise. I mean, our samples was the superposition of background noise and a wave packet with fixed shape. So if we increase the strength of the background noise, the information that this feature will give is reasonably smaller. But we can also get some less intuitive behavior. For example, if we consider this feature in which we just see the amplitude of we wait with the amplitude of the wave packet, we see that in some regions, this feature can be better than the previous one. And so we can distinguish different regions of our system in which different features are better to describe the system. In this case, we could also try to explain the reason why we get a larger renormalized mutual information. And this is because it is true that the square, weighting with the square of the field, is more sensible to the position of the peak of the wave packet. But in this case, we are also able, if we don't put the square, to average the noise, the background noise out, because the background noise that we were considering had a zero mean. So this averages out and gives us a better feature in this case. But we can also make a further step and ask, instead of proposing some features, try to find the best feature that describes our system. For example, we can parameterize a feature with a neural network, which is known to be able to approximate any kind of function if we make it powerful enough, and then to perform gradient ascent and choose the feature that gives the largest mutual information with the system. And we implemented this, for example, with the distribution that we were showing before. And this is the result that we get if we optimize using renormalized mutual information. We see that this is a feature that increases in the direction along which the distribution takes place, but also we see that there are some fluctuations in the regions where the probability distribution is almost zero. This can be also improved if we consider the results of more than one neural network. For example, you average over more than one neural network, and we see that there is, in general, agreement. This is the standard deviation among the results over different networks, and we see that in general they agree in the region which has the largest probability, while there is some fluctuations in the region that usually are zero. So the neural network looks at less samples, so it's harder to get it right. But it's also less important because we have a smaller probability to have the situation. So to sum up, the message is that if we want to build a representation of a physical system that lies in a smaller space, like to extract a few quantities that describe our system, we could think to use mutual information to characterize these features as the one that preserve the largest information with the system. However, we cannot use the usual mutual information because with deterministic and continuous features, this always diverges. And so what we have to do is to consider this other quantity, which in some sense behaves like mutual information, but does not diverge when we put a continuous feature. And we believe that the use of this quantity can be useful to make a simpler description of a system, and perhaps you could be able to make some prediction in cases in which if you just look at the high dimensional at a lot of coordinates, it's very hard to make. While if you consider a smaller representation, you may get a partial description, but which is still useful, even if it's just partial. You could get some intuition on the system, some insight like happens in fluid dynamics or thermodynamics. And with this, I would like to thank you for your attention and leave time for some questions.
Thank you, Leopoldo. We now have time for questions. Please feel free to use either the questions box or if you have raised hand, we can also see that and unmute you as well. So now I have one question coming in from the questions box. Let me read it out. When you use neural network, how do you train it? And after all, you don't know the features, so what do you use for target variables?
What I use to train the neural network, I am using a neural network to parameterize the feature. So what I'm doing is that I calculate mutual information between our neural network. I mean, we just need the neural network and we can calculate this mutual information, renormalized mutual information, which is the difference of those two terms that I was showing before. It's this quantity here. So y is equal to f of x. So we calculate the entropy of y, where y is the feature, and this other term here, where here is the gradient of the feature. We know that neural networks are differentiable functions, so we can calculate the gradient in an easy way. So we can make an estimate of those terms and perform gradient descent on those. This is the idea.
Thank you for the answer. So the question was asked by Honorkan, and Honorkan, I actually just unmuted you. Let me see. You seem to be self-muted. If you want to also interact with the presenter, you can unmute yourself. Oops. Okay. He said thanks for the answer. Let me move on to the next question, which is asked by Harrison Prosper. Is the mutual information in some sense a loss function?
In this case, in the context of feature extraction, yes, exactly. It's I mean, in some sense, the opposite of a loss function, because you usually minimize it, while in our case we are maximizing. So yes, we can say that the opposite of renormalized mutual information is the cost function on which we would optimize our f of x, which is parameterized for a neural network, to get the optimal one. Yes.
Awesome, thank you. Let's see if there are other raised hands. Again, if you have any question, please, you can also raise your hands. So we have one more question from Kevin Shen. How does this compare to variational autoencoders?
Well, there are lots of kinds of autoencoders, and okay, variational autoencoder is a kind of that. But the point is that in this way, we are not fixing the shape of our representation by being able on accomplishing some tasks. Like in the task of an autoencoder, you usually want to reconstruct your input. In this case, we are characterizing the bottleneck, what you get in the representation that you get, just by its properties of preserving the best information, the best that you can do, the largest information that you can do with the input. It's possible that autoencoder also maximize that or go in that direction, but of course that would be, we would need to prove that indeed they work well. Perhaps this is the reason.
Great. I see a raised hand from Peter Liu. I just unmuted you.
Hi, I had a question about the features that you extract. Since you can reparameterize it, how do you know you can, how do you interpret what you get? You can theoretically, you can say that since you can do any invertible transformation, it could be quite a wide variety of features.
Okay. Hi. This is also, I mean, it's also an advantage in some sense. I mean, you could also use this degree of freedom that you have to put some extra constraint that you want to put. I mean, it is true that you can perform an invertible transformation, but this is only on the feature space, this Y space. I mean, in principle, usually you have a high dimensional space X and a low dimensional space Y. The invertible transformations in Y you can do, and the mutual information won't change. But mainly the point is that what you want to extract is the connection between this high dimensional space and the low dimensional space. So this is the idea. After you extracted it, you can represent as you want.
All right, thanks.
Thank you for the questions and answers. Let's move on to the next speaker. We have Samuel Kim from MIT. Let me make you the presenter, Samuel. And Samuel Kim is currently a PhD student at MIT, working with Professor Marin. So I won't try. His research focused on computational design of optics devices and applying machine learning to physics discovery. So I will hand it to you, Samuel.
All right. Can you hear me? Let's see my screen.
Yes.
All right. Yeah, thank you so much for the introduction, and thank you to the organizers for putting this together. So my name is Samuel Kim. I'm a PhD student at MIT, working with Professor Martin Soljacic. And today I'll essentially be talking about how to make deep learning a little more useful for scientific discovery and exploration through a tool called Symbolic Regression. So first, I'd like to acknowledge my co-authors, as well as the many people that we've had discussions with. And at the bottom, I also like to acknowledge my funding sources. So first, we know that deep learning is extremely powerful in a wide range of domains, including image recognition, machine translation, image generation, video captioning, and most recently, an amusing paper that I found is guitar amp distortion simulation, which if you know guitarists and how picky they are about their amps, this is actually quite a formidable task. But of course, deep learning also has its downsides. They tend to be black box models, so they're difficult to interpret and look under the hood of what's going on. And they usually fail to extrapolate outside of the training regime. And both of these characteristics make deep learning difficult to use for scientific discovery and exploration. But a lesser known tool in machine learning is symbolic regression. So symbolic regression tries to fit a data set using some kind of analytical equation, usually built up of simpler functions. So here I'm showing this equation here. We have exponential, cosine, sine, and so on to build up this equation that then describes our data set. And the nice thing about this is that it's interpretable. We can see what's going on. And if you find the correct equation, then it's going to extrapolate well outside of your training regime. However, this is typically implemented through genetic programming, which makes it difficult to integrate with deep learning unless you do some kind of multi-stage approach. So in comes the equation learner, or EQL network, which has been proposed a couple years ago and also developed independently in our group. And it's mostly similar to a conventional neural network, feed-forward fully connected, where you have some kind of input X, you multiply it by a weight matrix W, and that leads you to a set of hidden units, G. Now, in a conventional neural network, you usually apply some kind of nonlinear activation function to these hidden units, such as ReLU, tang, sigmoid, and so on. But in our case, we're actually going to apply different activation functions to each hidden unit. And these activation functions are going to be our primitive functions. So these can include identity, squared, sign, and even multiplication, which takes in 2 inputs. And now we can stack multiple of these hidden layers together. And by stacking multiple of these layers together, we can now have an output which consists of a very complex combination and composition of these primitive functions. And by reading off the weights, you can get your analytical expression that describes your data set. And the nice thing about this is that because it's in the neural network paradigm, it is differentiable, and thus you can train it with backprop and integrate symbolic regression into deep learning. So this is essentially doing symbolic regression. As an aside, I'd like to note that one of the key ingredients to making this work is sparsity regularization. So normally you don't want all of your weights to be non-zero at the same time, because otherwise you end up with a very complex and unwieldy expression to describe your data set, and it's not very helpful. So the way that you do this is you put some regularization on to make the network as sparse as possible. This has been explored a lot in the context of neural networks. In our case, we played around with L1, L-half, and a relaxed version of L0 regularization. And we find that they're quite successful in only turning some of the weights on to keep the final expression as simple as possible that describes your data set. So now we can integrate symbolic regression into deep learning. We demonstrate this on several tasks. So first is MNIST arithmetic. So MNIST is a very famous data set consisting of images of handwritten digits ranging from 0 to 9. And so the task here is, say we take a pair of these images and we want to do some kind of arithmetic task on them, such as adding them up. So here I'm showing I have an image of a 7 and an image of a 5, and I want to output 12. Well, deep learning is especially suited for this task because of its strength in image recognition using a architecture called convolutional networks. So to tackle this task, we built this architecture that I show here, which consists of 2 convolutional networks here and here that share the same weight, that take in the image. And these are going to be what I call convolutional encoders. They feed into the latent variables, Z1 and Z2, which then feed into the EQL network. The key here is that the entire thing is trained end to end. So I'm not putting any sort of inductive bias on the latent variables. I'm not feeding in the labels 7 or 5 anywhere into the network. I'm just feeding in the images, feeding in the label at the end here, y equals 12, and training the entire architecture using backprop end to end. We also expect that the latent variables will somehow extract the labels or extract something meaningful out of these images. Looking at some of our results, first I'm showing after training what the latent variable looks like. So here I'm plotting, in the lower left, I'm plotting the latent variable as a function of the true digit, and we see this nice linear correlation between the two. Of course, with some scaling factor, because as I said before, we're not putting any kind of inductive bias or any extra information on our latent variable. So our encoders are successfully able to extract out some information about what the digit should be. On the right, I'm showing the predicted sum, the output of the architecture as a function of the true sum, and we see that nice one-to-one mapping. So we're able to train this architecture. And finally, if we read into the weights of the EQL network, we see the predicted equation here, which clearly shows that it's able to infer the additive nature of the arithmetic that we did to get the label. Of course, as I said, there's some scaling factors here because of the scaling from the latent variable. Now, perhaps more interestingly is how well this architecture is able to extrapolate. So to test this, I have a slight variation on the same task where I have a training data set. I can pull the images from the full range of the MNIST images, but I only keep the pairs where the sum is 14 or less in the training data set. For my test data set, I essentially do the opposite. I can pull all the images, but I only keep pairs where the sum is 15 or greater. So in some sense, the training and testing data set are mutually exclusive in terms of the labels. I trained the same architecture from scratch, end to end, but I also trained a variation of this architecture where I replaced this EQL network here with a conventional neural network, so it's fully connected, uses ReLU activation functions, and compared their accuracies on the training and testing data sets. So here, I'm showing the table of the accuracy. So on the training data set where y is less than 15, the networks reach 93 and 92% accuracy, so they're able to predict quite well. However, on the test data set, where y is greater than or equal to 15, the conventional neural network only reaches a 0.8% accuracy, whereas the EQL network is able to reach an 87% accuracy. So this shows that the conventional neural networks, conventional deep learning, completely fails to extrapolate outside of the training data set, whereas the EQL network is able to extrapolate quite well. Moving on to our next tasks to demonstrate this EQL network, I move on to dynamics extraction. So here I'm showing a couple of physical systems. The first is kinematics, just 1D acceleration, and the second is a simple harmonic oscillator. In both cases, we want to predict the position and velocity as a function of time over multiple time steps. And in both cases, we have an uncontrolled variable. In the first case, it's the acceleration. In the second case, it's omega squared, or the resonant frequency squared. And so these uncontrolled parameters will vary across the data set, and the architecture does not have access to these parameters, but we basically ask it to extract out those parameters. So here's the architecture that I use. As before, we have some kind of encoder where we feed in position and velocity as a function of time, and we expect it, this encoder uses convolutional layers, and we expect it to extract out something meaningful about that uncontrolled variable. So that goes into this latent variable Z. This Z then goes into a recurrent version of the EQL network. Now, recurrent neural networks are another type of deep learning architecture that are especially well suited for sequences such as language, text, audio, or even video. And the way that it works is that you feed in some input to your cell, which in our case is going to be this EQL network. And you take the output, and then you feed that output back into the same cell, and you do that over multiple times, so you can get a sequence of outputs. Another way to look at it is that you take that output, feed it back into the same cell, kind of like in a for loop. This depiction here is just an unrolled version of that recurrent architecture. And again, as before, there's no inductive bias or extra information fed into this architecture regarding the acceleration or omega squared, and the entire thing is trained end to end. Moving on to the results. So if we look at what happens to the latent variable, we see, again, a nice one-to-one mapping between the latent variable and our true parameter, showing that it's able to successfully extract out something meaningful about that uncontrolled parameter. And second, if we here I'm looking at the predicted dynamics, so that I'm plotting the position as a function of time, where in green is the true solution, orange is the prediction of the EQL network, and purple is prediction of a slightly a variation of this architecture, where, as before, I'm replacing the EQL network with a conventional neural network, fully connected radio activation functions. I'd also like to note that I'm only training it up to a certain time step, but when I'm plotting these, I'm asking it to predict out past that time step. So it's essentially extrapolating out beyond the training regime. So we can see that within the training regime, both the EQL network and the conventional neural network are able to match the true solution quite well. But once you ask it to extrapolate, the conventional neural network completely fails to replicate the dynamics, whereas the EQL network still matches the true solution very well. And I don't show it here, but if you read off the weights from the EQL network, you can back out the propagating equations, which in the kinematics case are these kinematic equations. In the harmonic oscillator case is actually a finite difference approximation of these differential equations here. And so to conclude, we can integrate symbolic regression neural networks in deep learning architectures, such as convolutional networks, encoders, and recurrent architectures. And we showed this on several tasks, such as MNIST arithmetic and dynamical system predictions. The key is that the results are interpretable, and the model can extrapolate well outside of the training regime, making this potentially useful for scientific discovery and exploration. And to conclude, I'd also like to note that our results are up on arXiv. We have a paper under review, and that we've also published the code online on GitHub. Thank you.
Thank you, Samuel. You finished right on time, so now we have time for questions. So I saw one question from Chris McCarthy. Did you use packages like TensorFlow, or did you build everything yourself?
Yeah, everything's using TensorFlow.
Cool. Thank you. So moving on, next question from Harrison Prosper. Isn't the failure of the neural network simply due to the fact that it models something different from the EQL?
I'm not exactly sure what you mean by modeling something different, but the neural networks in general, you can think of them as fancy extrapolators. So if I go back to, or sorry, fancy interpolators. But if I go back to these plots here, we can see that we're feeding in a position for the training regime. The position is going to be somewhat restricted to like 0 and -5, right? Once you get to a position of -10, the neural network has never seen that result before or that input before. So it's going to give you basically bogus results.
Okay. Harrison, I don't know if this perfectly answers your question. I now muted you. Do you want to speak up?
Oh yes. So yeah, I think there is a difference. I think that the if you look, as you well know, if you actually look at the loss functions that are typically used to train neural networks or any of these systems, then one sees, of course, that in the end these models are basically functions or functionals of probability densities. And so it is not surprising that if you then supply an instance that is far removed from the support of the probability density, these things are going to fail. And as you well know, for example, there are many instances in which you, let's take the MNIST data set, right? You change a single pixel to some crazy value. And because these neural networks are modeling probability distributions, then by simply changing a single pixel, you're moving an instant far away from the bulk of the probability density, and it's not surprising that they fail. But I think the difference here with your fantastic EQL is that what you're actually modeling, I think, is that you're modeling mathematical operations. So in some sense, on your slide 11, you're basically modeling a plus. But what is fascinating is you're modeling a plus directly from the images of these of the inputs. And so it doesn't surprise me at all that you could get a catastrophic failure with a neural network, whereas you do not, because in some sense your EQL has modeled the right operation, namely addition. Mm-hmm. So I think one has to be very careful in comparing these different models because they are actually modeling different things.
Sure. No, I think that's completely fair. I mean, I think the key is that the EQL network, I think the key is that we're essentially introducing some sort of inductive bias, right, into the EQL network, or that's what makes up the EQL network. And we're basically assuming that, a lot of these physical systems or the MNIST task is going to be able to be described with these arithmetic functions. Right?
That's right, yeah.
Right. So there is, I guess, some sort of prior knowledge in that sense.
Yeah, and I think that's great. And I think this is really a fantastic thing because indeed, as you correctly pointed out, this is one of the problems with the current deep neural network models, or in fact any of these models, is that since they are modeling probability distributions, then necessarily, obviously, they will fail if you present it with an instance that is not a sample from the probability distribution that they are modeling. And this is why I'm more surprised that people are shocked when these systems fail catastrophically. That's what you expect.
Right.
If you model the correct operations, if you inject knowledge about the nature of the functions you're trying to model, as in, for example, your beautiful dynamic system here, then for sure it will extrapolate because it's actually got the right answer.
Right. Right. Exactly.
This is very nice.
Yep.
Thank you.
Yep. Yeah, so thank you, Harrison, for the comments. We have several more questions. Let me try to squeeze them in. So Stephen Torrisi is asking whether you have tried to introduce noise into the input trajectories, or in other words, did the regularization take care of noise or to avoid overfitting?
Oh, sure. So we haven't explicitly introduced noise, but I think one interesting thing here is if I look at the dynamics result for the simple harmonic oscillator, the latent variable extraction is somewhat noisy. And this is just one of the cleaner runs. We do this over multiple trials and we get much noisier results here. But it's still somewhat noisy, especially towards the end. And the EQL network is still able to extract out the correct dynamics. And a lot of that has to do with this sparsity regularization that we put on the EQL network.
Awesome. Yeah. So Scott Hawley asked a question regarding a prior work that Schmidt and Lipson did in 2009, but they didn't have neural network feature extraction on the front end. So could you make explicit for us non-specialists how your EQL differs from their symbolic tree method?
Sure. I think I know the paper that you're talking about. The key is that they're using more traditional symbolic regression techniques. And as you point out, they're not interfacing it with any deep learning methods. So they're basically putting the symbolic regression directly on your data set. So there's no unknown or hidden variables or anything to extract out. The other key is that their symbolic regression, as I mentioned, uses genetic algorithms, which are typically computationally expensive.
All right, thank you. So with that, I really want to thank you for a fantastic talk. And in the interest of time, let's move on to our third speaker, William Mitchell. Let me try to get William speaker right. William Mitchell is a recent graduate of Belmont University physics program in Nashville, Tennessee. He graduated with a bachelor's in both physics and audio engineering technology, and he tries to meld these two fields in his deep learning research. He plans to attend the University of North Texas physics PhD program in the fall. So welcome, William.
Thank you. Can you see and hear me all right?
Yep.
All right, thank you. Yes, I'm William Mitchell. My talk is titled Signal Train Continued, Modeling Time-Dependent Nonlinear Signal Processing Effects Using Deep Neural Networks. This research was done under the guidance of Dr. Scott Hawley at Belmont University's Department of Physics and Chemistry. So to get into it, in many areas in physics, as these talks have kind of gone over, neural networks are providing a data-driven path toward modeling complex phenomena. In our case, we're specifically trying to model electronic circuits and or acoustic behavior. This falls under the branch of effects modeling, more specifically nonlinear time series modeling, things like compressors or things like guitar amp distortion, which received a wonderful shout out by the previous presentation. So we focus on linear effects mainly because, or nonlinear effects, because linear effects can be modeled using finite impulse responses. They maintain additivity and homogeneity from input to output. Nonlinear effects are just anything that don't maintain these two things. In our experimentation, the only assumption we're really making is that this behavior can be modeled in a characterized in a finite time frame. Right now in this field, current experimental standards are using spectrograms as input and output data, 16 kilohertz sampling rate as the audio, and there's not really a file format standard, although MP3 and waves are the most common. And then often very short audio clips of very limited material are used both in data sets and to demonstrate network capabilities. So what we're trying to do with Signal Train is move towards the waveform domain and try to use as high quality audio as possible. We think the waveform domain is important because it contains time, frequency, and phase information, which spectrograms alone cannot. Spectrograms can maintain magnitude and frequency information over time, but they completely ignore any kind of phase characteristics the audio might maintain. Moving to the waveform domain does mean the need for increased computation power, although with the increase in computation power in consumer products over the last couple of years, that is becoming less and less of a problem. And we can expect that to be less and less of a problem in the future. We also want to use high quality audio, so higher frequencies can be represented with higher sampling rates. Right now, CD quality audio is 16 bit depth at 44.1 kilohertz sampling rate, and that's what we're trying to shoot for with the audio we use. So kind of to go over our task, our objective was to model characteristics of signal processing effects and their parameterized controls in a model-agnostic manner. And we conceive this task as a supervised learning regression problem performed in an end-to-end manner. In this diagram on the left, you can see we kind of have two parallel streams. We have input audio going through an actual audio effects unit. And these audio effects units are parameterized by different knobs. Much like a radio can be tuned with a knob, a lot of these audio effects can be tuned with multiple different knobs. What the knob does depends on what effect and from what manufacturer, but that produces our target output audio. We take the same input audio, we feed it through our neural network, and we can also parameterize our network using virtual knobs. You can set how many knobs you want, you can set minimum and maximum values. And so what we're trying to do is not only model these effects, but model these effects that can have their settings changed. You can model a specific effect, change the setting, you'll get a different output. So our network produces the predicted output audio, and our goal is to minimize this difference between the target and predicted. This is going to be a pretty basic overview of our architecture. Signal train is comprised of front-end and back-end encoder-decoder configuration in an hourglass form modeled after the UNet architecture, and operates in both time and frequency domains explicitly, modeled after the TFnet architecture. And so on this picture on the right, you have the input, which is, again, parameterized by our controls, or these virtual knobs. We have two 1D convolutional layers that produce our magnitude and phase characteristics. We send these both simultaneously through 7 fully connected layers. Again, all the while being parameterized by our knobs. We reverse the process at the end to produce our output, and we match that against our target audio. So we kind of took a 3-pronged approach in our current research, trying to improve or explore the accuracy and noise of our model, the generalizability, and the speed. With accuracy and noise, our baselines were averaging around 7.15 e to the minus 6 on a log Cauchy loss function with L1 regularization. This number alone may not mean much, but it's a good way to compare the model trainings to each other. And we focused on this comp4C effect, which is a digital compressor with 4 knobs. For these baselines, we had noticeable noise in outputs. It did sound like the model was training on a compressor. It did sound like a compressor was working, but there was a noticeable noise floor. And then generalizability. So this comp4C effect, or this digital compressor, was the only effect rigorously tested, and we used mainly randomly generated data sets. And with speed, our baselines with 200,000 data points and 1,000 epochs averaged between 12 to 13 hours. So 2 approaches to trying to increase our speed was by freezing our Fourier transform layers and removing skip connections. So our Fourier transform layers throughout the model are updatable as they go, and we thought they might be computationally expensive and not sure how accurate they are making the model. What we found was that by freezing these layers, they were no longer updatable. We could achieve a little bit of a faster training, 11.56% faster, but we lost an order of magnitude in loss function. We were 10 times less accurate. And there may be a trade-off between getting faster and less accurate, but we thought you would have to be much, much faster to justify a loss of an order of magnitude. And then removing skip connections. And so we thought that the final skip connection across our model might be the most computationally expensive to maintain. What we found was that this final skip connection adds essentially 0 time for training on this baseline compared. They both averaged exactly 12.81 hours actually. And it increases our accuracy by 24.4% on the training set. Here's the results on the validation set. And so all these graphs will be showing our log graphs. You can kind of view them as loss value over time. Loss value, the lower the better. So epoch or time on the x-axis and loss on the y-axis. So these are the skip connection results. And here are the frozen transform layers results. As you can see, there's a much bigger leap. Here, about an order of magnitude between the baseline and the frozen layers being much, much worse. So looking into this accuracy and noise, the first thing we want to do was test the limits of our baseline model just by running it for much longer than we usually do. And then we wanted to test data set content. So the first thing we did was lock the knob ranges. So instead of being able to set the knobs at some minimum value and some maximum value and having the model choose between the two, we locked the knob ranges to one single value. Should be theoretically a simpler task. And then we had a couple of new data sets that we were using. A music-only data set that we used as our baseline, and a vocals-only data set that contained just a cappella vocal audio, no instrumentation, no noise. And then we took that same data set and downsampled it to 16 kilohertz sampling rate. And there's actually recent commercial viability for these data set specific runs. And NVIDIA released something recently called the RTX Voice, which is used in things like podcasting or streaming, that is able to recognize the human voice and essentially denoise anything that's going on in the background. It doesn't pick up anything other than a human voice, ideally. And so looking at our long trainings, in orange is the 1,000 epoch training, and then in red is the 10,000 epochs. And what we did find was that we could achieve a slightly better validation loss over this longer time. We trained for about 130 hours on this one. Where the output quality of the audio saw no noticeable improvements. Again, the compressor effects sounded to be modeled correctly, but the noise floor wasn't dropped significantly or noticeably enough to warrant training for such a long amount of time. Furthermore, these are the results for the different data sets. Baseline at the top, and we also actually saw a pretty good jump in loss value for the vocal-only data set at 44.1 kilohertz. It should be noted that the vocal only at 16 kilohertz did train for about an hour faster or an hour less than the other two. Although at 16 kilohertz, the lower sampling rate, there's less data that would be expected. And I think this vocal only result is interesting, not only because we could have tightened the data set even more. The data set we use for vocals has both male and female. I think it even has different languages, both talking and singing. And so there's definitely more you can do that could restrict the content of the audio in the data set that theoretically or ideally could push that loss value lower. But this does bring in a balance between loss value and generalizability. What we found with our noise was that matching input test audio to a model trained on similar data set contents is the most important aspect of output quality. For example, these two waveforms on the right are output waveforms of a model trained on just guitar notes. So when you train a model on just guitar notes and you give it a guitar note like the one on the top waveform on the right, what you get is something that sounds like a guitar note that's been compressed. There's very little noise, very little distortion. However, when you give this same model a full song, there's anywhere where you see that purple color reach the top and the bottom is full distortion, and almost the entire song is fully distorted. The model doesn't know what to do, and this I think ties in nicely with the extrapolation problem we were hearing about earlier. And so there is a balance between this diversity or generalizability of these models with their loss value. Data sets with more diverse contents provide greater generalizability. They work on a more wide range of audio, but they might not achieve loss values as low as those models that trained on very specific tasks or very specific audio contents. Looking further into this generalizability, we wanted to expand our effects library. Previously, we focused on just compressors, mainly because they proved to be the most difficult, although this current research expanded into limiter effects, tremolo, chorus, and preamps. And then we also wanted to work or cover both the digital and analog domains. So analog effects, the LA2A compressor and the Leslie cabinet, which are both pictured below, are analog effects. And we kind of covered the digital domain already with this 4-knob compressor and our 1-knob compressor. So these new effects, we used a data set constructed by Marco Martinez Ramirez from Queen Mary University. It contains 2-second electric and bass guitar notes for the IDMT SFT audio effects dataset as dry samples. And you can see the results on the bottom. It should be noted, that the training times are much longer because for this Leslie cabinet, it has a rotating horn within it, and this produces oscillatory characteristics in the effect. And in order for the model to train even reasonably well, the input audio length needs to be long enough to cover an entire oscillation. And that just means that what you're inputting into the model must be much longer, because there's a lot more data for the model to cover, and so the training times you expect would be significantly longer. What we found here was that we could get good quality output, but again on very limited audio content. It really only worked on guitar notes that were about 2 seconds long. And I think this is a good opportunity to try and improve values through effect-specific tuning. You can see kind of a pattern developing in just these 4 results. Both horn effects had a better validation set loss than both woofer effects, and the horn effects are just high frequency content mainly. Woofer effects are low frequency content mainly. And then on our training sets, we actually achieved loss results that were as good, if not better, than our baseline training sets. But in our training sets, we had both chorus effects trained much better than both tremolo effects, which is interesting behavior that might warrant further research. And so to kind of conclude, we have code available on GitHub under Dr. Scott Hawley's Signal Train page. This contains both a Jupyter Notebook or Google Colab demo, which you can see kind of pictured on the right. You can actually choose your effect, choose what type of input signal you'd want. We have minimum and maximum ranges for our 4 knobs for this specific effect. And I think it's really cool. You can change how the input audio will look and how that affects both the predicted and our model's targeted output. And then finally, we've also recently uploaded an original data set titled Signal Train Concatenated Dataset, just to kind of document and provide any audio we used to generate these results that wasn't already available in a previously constructed data set. Either our Signal Train LI2A data set, or although we use audio from the FMA data set, TensorFlow's NSynth data set, and the data set from Queen Mary University, as discussed previously. So looking to the future, continued optimization, bringing in more state-of-the-art and recently released methods. I think there's a good opportunity for effect-specific optimization. And this research is centered at Belmont University, which has a pretty large quantity of critical listeners in their music production program that I think provides a really interesting and unique opportunity to conduct really high quality listening and quality assessments. And then also we would love deeper audio plugin integration, something like taking a third-party digital plugin and being able to utilize it to produce audio within our network. Special thanks to Dr. Scott Hawley again from the Department of Chemistry and Physics at Belmont University. Also to Stylianos Mimilakis for his help this past year at Fraunhofer Institute for Digital Media Technology. Belmont University's Department of Chemistry and Physics for giving us the space and the opportunity, and of course to APS for giving us an opportunity to present our research in such an interesting time. And then I think I should have at least a couple minutes for questions.
Yes, you do. Thank you, William. This is fantastic. So
Thank you.
I start to see questions coming in. So Florian Marquardt asked the question about the network processes. He said, I think you set the network processes both in the frequency and time domain. How does that work?
So we can look back to our kind of overview of our model. So what we're trying to do is we take magnitude and phase characteristics separately, and these both work sort of like magnitude over time and phase over time, and we model those separately into like kind of parallel streams into separate layers. I think that answers your question.
I see. Yes, it does. So let me see if Florian's online. Okay. Yeah, he said it does answer the question. So thank you for that. We have another question from actually Emily. She asked, how perceivable by human ear are the differences in the losses? Can we notice it? And what would be the use case gain by like going an order of magnitude to lower in the loss? Is it worthwhile?
Right, so that's actually a really interesting, like a really excellent question, because our ears are like so incredibly sensitive that you would expect very little changes in loss to mean a lot. Although it doesn't always turn out that way. There is a bit of a discrepancy between loss value and what someone might hear. So, for example, on our baselines, you would achieve something around 7e to the -6, right? And that would have noticeable noise, although it wouldn't be like overbearing. And with our baseline trained on a much longer, we got down to something like 3e to the -6. I personally, you would hear almost no difference. It would be almost the same exact level of noise mathematically, and our loss function would argue that there's less noise, but it is essentially imperceivable. While something like you could have, just for example, a loss value that is, let's say, an order of magnitude worse. So it would be 7e to the -5. Something like that could be almost like unlistenable. It would just, like the noise would dominate too much, or if there wasn't a lot of noise, it would be something like very distorted or very or no effect really present. There is an interesting, I think, intersection between art and science here, where not always, when the science says this model should be performing significantly better, it doesn't necessarily mean that you're going to hear that.
I see. Fantastic. Thank you for the answer. So let me conclude this webinar by on a higher note, looking forward to the next one. So first of all, thank you to all three of our fantastic presenters. I think we learned a lot today. And then looking forward for next week, we are going to have an upcoming special webinar. We are going to learn from Victor Baptist from Google DeepMind on machine learning glasses, and Victor will specifically discuss his very recent article on Nature Physics on how to unveil the predictive power of static structure in glassy systems. So if you hold up your phone to the screen and towards the QR code, you should be able to get redirected to the registration page. And we will be also sending this out to our mailing list as well. So thank you for attending the webinar today, and looking forward to see you in the future. Okay.